deal with too.
Good morning. This is basically about IPv6 over PPP. I'm here to speak on behalf of the Greek Student Network. The Greek Student Network is a collaboration of many different peers within Greece. All these peers are being, the main administrator here is the Greek Research Network, which does all the coordination among those peers. So here's how EduDSL. I'm going to be calling the Greek Student Network EduDSL from now on. Okay, this is basically a normal DSL deployment. The user is forwarded to our LNSs. The LNSs are being administered by the Greek Research Network, and the uplink is provided by the Greek Research Network. The user is being forwarded with PPP over L2TP to one of our LNSs. The authentication requests go to a proxy radius. Proxy radius is also being administered by the Greek Research Network, the authentication, the proxy radius assigns all the addresses, be it IPv4 or IPv6, and then, but the authentication itself is being done by several ISPs. These are commercial ISPs that handle all the billing, user registration, everything of this administrative domain. Okay. So the present status is that the EduDSL, the Greek Student Network, services students from like 50 academic institutions within Greece. This is about like 30,000 users. The important thing to note here is that each user has a particular affiliated institution. So this user must receive an IPv4 or IPv6 in the future, right? An IPv6 from his or her affiliated institution. This is important because, you know, each institution has various agreements with libraries and other organizations. So it's very important that each user receives an IP address from his institution. Okay, for account management, billing, and accounting, and all those sorts of stuff. There are, at this point, 3 commercial ISPs that are collaborating with the EduDSL organization. Okay, like I said, the Greek Research Network provides all the connectivity, all the administration, and of course, the Greek Research Network buys all the equipment. At this point, the equipment are 9 Cisco 7300 LNSs. They are connected to the Greek Research Network backbone by using 3 gigabit uplinks. This can be upgraded at will if we see fit to, if the Greek Research Network sees fit to. And of course, there is also the administration of 2 proxy radius servers, which are set up in a redundant configuration. The objective is to provide native IPv6 over PPP to all these 30,000+ students. The problem with PPP is that you don't only have to enable IPv6 over the PPP, but you also have to enable IPv6 on the homeland behind the PPP, on the homeland of the user. That's behind the CPE. Of course, with IPv4 we had network address translation. With IPv6 this doesn't hold anymore. So there must be additional IPv6 global addresses assigned behind the CPE. Of course, we want to know which address each and everyone uses. So IPv6 accounting is also of paramount importance. We don't know the user to know that he actually uses IPv6. Ideally, I mean, it should be completely transparent. Nobody should notice anything. And there are also some complications related to the fact that all the students are from different institutions. So we must make sure that each student receives IPv6 address from his respective institution. Also, because the authentication and the billing is done by the ISP radiuses, which are not our proxy radiuses, we must make sure that our communication of our proxy radius with the ISP radiuses is unaffected. We don't want to break anything. And of course, we must make sure that all mainstream CPEs and Windows Vista over PPPoE or Mac OS X or Linux FreeBSD, everything works flawlessly with our infrastructure. Okay, the main thing here about the addressing scheme. Okay, the lowest 64 bits, let's not concern ourselves yet with it. The important fact here to note is that each institution delegates at least one /48 prefix to our infrastructure. This /48 we can use it as we see fit inside our infrastructure. Okay, since the user is going to be receiving one or more /64 IPv6 prefixes, that leaves us like 16 bits to allocate addresses to all the users within all the 9 LNSs. 9 today, maybe tomorrow it's going to be more. So we have decided to give 4 bits to assign as an LNS ID within the address, and then the remaining 12 bits leave a room of 4,096 prefixes per LNS per institution. Since for the devices that we are using today, which are, like I said, Cisco 7301, if I remember correctly, the capability of the 7301 is like overall 4,000 users per device. So 4,000 prefixes per institution per LNS gives us a lot of breathing space. It should be okay. Okay, the command on the bottom is how do you create the local pool that holds all the addresses per LNS? For example, here's the for example, let's take institution number 2. Institution number 2 has given us a /48 prefix on a specific LNS. Minus 4 bits comes to /52, which is divided into /64 parts. So the users get the importance. This may be confusing at this point. Okay. But the important thing to note is that all the users get /64 prefixes, either for the one link or the LAN link behind it. So a few words on how IPv6 over BBB. Most of you probably knows all about it. Okay, the LCP is completely unchanged, and the IPv6 CP, contrary to the NCP phase for IPv4, is much simpler because there are no addresses, no DNS options involved at this point. The only option that is being used, and please note that this is important for our infrastructure, is the interface ID, which are the lowest 64 bits that the CPE will be using to create his PPP IPv6 one address. This is essentially the EWE64 address, which all of you probably are familiar with. Okay, after the PPP establishes itself between the LNS and the CPE, IPv6 address auto-configuration is being done normally. Do note that the interface ID, which are the 64 bits, is being used as an EWE64 address to complete the address auto-configuration. And like I said, the recommendation is always to use /64 prefixes in all the interfaces around the CPE. Okay, the tricky part, that was easy. Okay, this is just IPv6 over PPP. The tricky part is to enumerate the home LAN behind the CPE. Okay, in our opinion, the ideal way to do it is to use RFC 4389, which is called ND proxy, neighbor discovery proxies, and basically with this method, one can use only one /64 IPv6 prefix to enumerate both the PPP1 interface of the CPE and the home LAN of the user behind the CPE. So this is pretty good because only 164. So we make a prefix economy at this point. But we're not aware of any CPEs that implement this feature at this point. So the usage of this feature is deferred for the future, unfortunately. So the best next option is DHCPv6 prefix delegation. I'm sure that most of you heard all about DHCPv6 prefix delegation yesterday in one of the afternoon's presentations. Basically, DHCPv6 prefix delegation works like this. The CPE, after the establishment of the PPP link and the enumeration of the PPP link with a /64 prefix, the CPE can request additional IPv6/64 prefixes from the LNS. It is our intention to use the same local IPv6 address pool within the LNS to enumerate, to give prefixes both to the WAN addresses and the home LAN addresses. So you can see here that the same IPv6 local prefix pool for institution 2 is being used to enumerate both the home LAN behind the CPE. Once the CPE requests and receives a /64 as it sees fit, it proceeds to issue router ND array messages within the home LAN, so all the other equipment inside this LAN gets to use this prefix. So, okay, a few words on how do you implement the enumeration of the PPP link and then the home LAN behind the CPE. Okay, first for the PPP link. We are interested in mainly in two ITF radius attributes. The first is the framed interface ID. The framed interface ID, like I said, is basically the lowest 64 bits of the address that is going to be, that the CPE of the user is going to be using. And then the framed IPv6 pool is the name of the local IPv6 address pool within the LNS that is going to be used to issue the neighbor discovery router advertisement inside the PPP link. So the LNS sends an access request to the radius. This is our radius. This is not the ISP radius. Please note that. And the access accept contains these two attributes. For example, framed IPv6 pool is the pool of institution number 2, and then the framed interface ID is a specific 64-bit address. And then the LNS, at least on our iOS version, which is, if I remember correctly, 12.3, the framed interface ID is also included in the accounting start and stop messages which are being sent by the LNS to the radio server. So, okay, this is pretty standard because we are using ITF attributes, so it's quite okay. The tricky part is for the IPv6 prefix, the DHCPv6 prefix delegation, which is done afterwards, because here our equipment at this point does not have the ability to use an ITF attribute to do it. So we have to set up here an IPv6 DHCP pool, which is the DHCP pool that will be serving the specific institution. Here it's institution number 2. Institution number 2 is the example institution. Okay, and then the command is to do prefix delegation based on the local address pool which we have mentioned earlier. To make sure that the CPE has the to make sure that the LNS has the instructions to delegate the correct address to the CPE, we have to use a Cisco vendor-specific radius pair, which is, like you can see, injects the command IPv6 DHCP server with the specific DHCP pool into the interface config of the PPP. Okay, that way we're using the same IPv, like I said before, we're using the same IPv6 local prefix pool, both for the WAN and for the LAN. And this is, of course, results to simpler configuration, uniformity, and more efficient usage of the available address prefixes that we have in our disposal. Okay, how do we deal with DNS? Most of you probably know all about it. There's RFC 5006, which is a way to inject DNS configuration inside the NDRAs. But okay, we'll have to wait for a little about this because it's not available everywhere. Okay, and also we'll be evaluating Anycast DNS in the future, although I don't feel that it's gonna work. Okay, all these methods are described briefly in RFC 433 and 39, as you can see. And okay, the way that we're doing at this point is the use of the other options flag inside the NDRA that is being sent by the LNS to the CPE. This is basically like it was said yesterday in the other presentation by Comcast. This is IPv6 stateless mode. You can insert the option DNS server and then the address, the IPv6 address of the DNS, sorry, the address of the DNS server inside the IPv6 DHCP pool. As you can see, the IPv6 DHCP pool here has the prefix delegation command, and then we also add the DNS server option. And this works quite well with the IPCP DNS settings, which are transmitted via the in the NCP phase of PPP. And of course, in the future, there is the capability to add other options. I mean, apart from DNS, like SNTP servers and other interesting capabilities. Okay, of course, we're interested in IPv6 accounting because we want to know which IPv6 prefix each one of our users receive, both on the one link and on the LAN behind the CPE. Okay, because at our iOS version at this point, there are some attributes missing. The only attribute present on the accounting messages is the framed interface ID. So framed interface ID is only the lowest 64 bits. So what do? We make sure that each user has a unique 64 interface ID. So when I connect to the EduDSL infrastructure, I always get my IPv6 address always has the 64 bits, the lowest 64 bits the same. So how do we do it? One simple way is to get the username and hash it by an appropriate hashing function to 64 bits, or we could in the future store these 64 IDs in a database. But at this point, we believe that there's no problem to using a hashing function. And this does not affect the home radiuses at all, because we can at will suppress the transmission of this interface to the home radius of its user. Sorry. So some problems we have encountered while researching all this stuff. Okay, the first problem is that, like I said, each institution assigns IPv6 addresses for its users to receive, and also each institution has the right to define a policy which is being expressed as an access list in the virtual template. The virtual template is the PPP interface connecting the user with the infrastructure. But we came upon this nasty bug, because when you try to use both access lists, named access lists, and IPv6 on the same virtual interface, the virtual interface doesn't come up at all. Because there is a name class between the IPv4 and the IPv6 access list name inside the LNS implementation of the Cisco iOS. So at this point we have a bug open with Cisco systems, and they will be, as they said, they will be implementing a new feature which would require the use of IPv4 : or IPv6 : in front of the IP access list inside the radius attribute that defines the access list. That is the filter ID radius attribute, if I remember correctly. Okay, one other problem is that if the client, the CPE, I mean, okay, if the client is crazy buggy or malevolent, there's this danger that it might request not only 1 or 2 /64 prefixes to enumerate the homeland, but many more. This is a problem because I mean this could lead to IPv6 prefix address exhaustion. So we would really like to have a way to resource to limit the resources assigned to each subscriber. And as I described earlier, of course there are some ITF IPv6 attributes missing from our current iOS version, so we have to resort to the usage of the framed interface ID, but we would really like to have all these attributes inside our accounting start and stop messages and update messages, of course. And okay, of course, the fact that we have to resort to vendor-specific attributes and inject interface commands each time a user PPP goes up is not too good because apart from other problems, using a interface command inside the Cisco EV pair disables the virtual profile cloning, which has a performance impact on PPP establishment in the infrastructure. But okay, we don't feel that this is mostly. I mean, we don't feel that this is too serious. Okay, but one serious problem is that at this point we have now we have found of no way to do DHCPv6 accounting. DHCPv6 accounting. So basically, we don't know which prefix your CPE received and enumerate the homeland behind it. So we can end up having users that we don't know the address they are using. So one question that might arise, and I've been anticipating this question, is why not use static IPv6 prefixes per user? And you know, in fact, this is quite logical because it would result into much simpler radius configuration. The DHCPv6 prefix delegation could be set up quite easily. And of course, the LNS implementation, which at this point is Cisco iOS, would not be that important. But please note that we have at this point 9 LNS servers, and this could go up in the future. And so, basically, when you don't know where where each user is going to end up, I mean, where the PTT is going to forward the L2TP session, you end up having IPv6 prefixes all over the place. And we believe that for the 30,000 and increasing students that we have at this point, we would have problems converging the routing protocol if we were to use static IPv6 prefixes. What's the current status? At this point, we have given out some IPv6 enabled test accounts to some individuals that we know of. There are some native IPv6 CPEs. There's this company, if I remember, called Billion. And of course, my main method of testing this setup is using Vista, Windows Vista, and PPP over Ethernet. Okay, we have already carried out the changes which are needed to be done to the proxy radius servers, so it's pretty okay on that front. And of course, Windows Vista, I must note that after Service Pack 1, Windows Vista works very good. Everything works flawlessly. When you enable the Internet Connection Sharing Agent and you have a it's broadband connection that is IPv6 enabled, which it is by default, the Internet Connection Sharing Agent just does DHCPv6 prefix delegation by default. User doesn't need to know anything or set up anything. Okay, where are we going from here? Of course, we want to fix the current problems that are that were described earlier. We're also toying around with the tunnel switch from Hexago, and this will be to accommodate all the users that won't have either PPP, Vista PPPoE or other PPPoE or even a native CPE capability. And we hope that within 2009 we'll fully IPv6 enable one institution, and then we'll monitor and fix whatever problems arise along the way. And in parallel, I had my hands on a Juniper E320. I mean, this is apart from the Cisco IDOS devices, which are the production devices at this point. And so I thought that you might find interesting some key facts about the Junos E, which is the operating system that the E320 uses at this point. It's quite interesting because, okay, see here, the framed IPv6 pool attribute, which is the ITF attribute, is usable to implement DHCPv6 prefix delegation. So this is quite good. Of course, there is also the delegated IPv6 prefix. This is also an ITF attribute, and this can be used to explicitly define the IPv6 prefix that is going to be used for DHCPv6 prefix delegation. But please note that the delegated IPv6 prefix, when using this attribute, we must explicitly define the IPv6 prefix exactly, not the pool. So for the one link, the PPP link, we cannot use a pool, an IPv6 local pool within the Juniper device, unfortunately. So in order to enumerate the PPP link with neighbor discovery router advertisements, we must use the framed IPv6 prefix. So we must define the IPv6 prefix explicitly. We cannot use the pool. So one would go with either one of these two approaches. The first approach would be to use the framed IPv6 prefix and the delegated IPv6 prefix. So all the IPv6 addresses are being managed by the radio server. So the radio server exclusively manages all the IPv6 addresses. The second approach, which is quite awkward, is to use the framed IPv6 pool to enumerate, to make DHCPv6 prefix delegation work, and then use the framed IPv6 prefix for the PPP connection. And this is quite awkward. Why? Because half the IPv6 addresses are being managed by the radio server, and then half the other IPv6 addresses are being used by the in a local IPv6 pool within the LNS. So I don't know. It's quite tricky. I don't know how it would be done at this point. We're still thinking about it, if we're going to use the Juniper device. Yeah, that pretty much concludes the presentation. Hope it was not too long.
No,
we're okay?
We're well ahead of schedule now.
Perfect.
Any questions? We have somebody is actually awake out there. I'm so happy.
Mike Joseph, Google. Regarding static assignment, it sounds like your primary concern was propagating the route information across your multiple LNSs and IGP convergence. Have you considered running BGP from the LNSs, which should do better at managing that size routing and that level of churn?
Yeah. Okay. Basically, this whole scheme. Can you hear me, right? Yeah. Basically, this whole scheme was designed like 3 years ago by our router guys. I'm mainly an access guy, but I'm going to answer. You mean that? I mean, the thought. We haven't really considered BGP, but we have considered using separate OSPF areas for each LNS. I mean, okay, each LNS and its uplink is on a different OSPF area to minimize the routing updates that are being done. So when a prefix comes up in LNS1, all the other LNSs don't need to know about this update, which is basically the same thing that we are thinking about BGP. Am I correct?
Well, yes and no. I mean, BGP handles that level of churn quite a bit better than an IGP does. Is there a specific reason you can't use BGP in your application?
At this point, I'm not sure that I can answer it because it was decided right before I entered the IPv6 enabling of this project.
Thank you.
Go ahead.
Could you speak a little bit about the CPE routers that you're using?
Yeah. Like I said, all my experiments, all the tests that I have done so far. Sorry. Did I do that? Okay, I have experimented with Windows Vista and a PPP over Ethernet configuration, and I'm waiting for some IPv6 enabled CPEs from a company called Billion to arrive and do some tests.
Okay, so you haven't played around with any Linux-based or...
Yes. No, it works. It works. This guy, Alexandros Kosiaris, has been playing around, and he also set up a FreeBSD client, and it works. And might I say it worked better, because when we started playing with this thing, the Vista implementation had some buggy DHCPv6 DHCP prefix delegation behavior, but we were able to, configure our FreeBSD right away to request only one prefix and work perfectly.
I was primarily wondering if it had suddenly become possible to buy stuff that actually works off the shelf easily, and I guess the answer is not quite yet.
I agree with you. It's not
you.
quite there yet. I think that also Zyxel has some IPv6 enabled CPEs. But
It wouldn't surprise me to see it in something like DDWRT or OpenWRT either, but the Zyxel obviously is going to be easier for support, right? Because you actually have someone you can call.
Yeah, I agree. I think that, as you can see in our presentation, we had some more serious problems than worrying about making every CPE playable. Because, you can see that for quite some time we had problem with enabling IPv6 because of the IPv4, IPv6 access list name class, which prevented us from doing any real tests on the production infrastructure.
Thank you.
Martin Levy from Hurricane Electric. There's a general mindset in the V6 world that auto-configuration makes everything very easy on the V6 side, and you've proven it isn't. I'm okay with that.
I'm also okay with that.
Okay. But I want to talk to you, ask a question about monitoring, relating customers between your V6 addresses and your V4 addresses. You have I'll put this politely, you have a student body as your user base, and there is a mindset that every now and again that causes a little bit of a problem, whether it be rogue laptops or software or whatever within inside that large community that you have non-IT style control over. What have you done for monitoring over and above all of the work that you've done from the DHCP side of the world, but what have you done for monitoring and relating traffic between V4 and V6 clients based upon the level of complexity that you've built onto this? And then my second question, and I'll go sit down, is can you just talk about traffic levels and where you see that going, at an aggregate level over all of your work?
I'm not sure that I understand the question. If you are asking about what is the ratio, are you asking about the ratio between IPv4 and IPv6 traffic?
No. I was just talking about, it's a general question. Take it second as general traffic levels that you're actually seeing from your customer base. But the first one's the more important. The first one's the more important.
Yeah, sorry.
Yeah, the first one's more important in the sense of how do you map between and look after.
Here's the traffic level.
I don't have eyes for that.
Okay,
I'll come up and look. Okay, that's fine.
it was like 3 megabits like some months ago. At this point, it's much larger.
Okay. So the first question is, so how are you doing your mapping and looking after and seeing whether you've got issues with your customer base between the V6 addresses that you see, the V4 addresses that you see, and the tools that you had for V4 and how you're dealing with those in the V6 world?
Yeah, that's a good question. It's quite tricky actually to do it because, but it's not. I don't think that it concerns me only because access services are always tricky because you have end users. So even the slightest thing you do affects users. And if you and me were talking, we would communicate quite easily. I would run pings, trace routes, or whatever, and see what's happened. But the user, exactly like you said, the user is mostly, at the worst case, the user is clueless, right? So this is a problem. When we started doing some tests, it was a horror story indeed, because we, after 2 or 3 days, we saw that some users could not connect. And then we identified the IPv4, IPv6 name class. There was no way for us to know that in advance. These are serious problems, and I totally agree with you, and we don't have a magic method to know if some users are having a particular problem or not. But I believe this is the general case with access services. Access services, I think, are the most tricky part to, most tricky to troubleshoot. If I cover your question, right? Yep.
Anton Capella of Voxel.net. I'm curious if you could perhaps expand some of the data in this presentation, perhaps an update to the slides, or something to the NANOG users list to include perhaps a few relevant snippets from your virtual templates. I think that might be helpful for folks to see how at least your deployment has utilized combination of AV pair from Radius as well as local pool on your LNSs. I think the snippets we saw were good. I'm genuinely curious though about anything you've done with any perhaps MRRU auto detection. We've seen some issues with this across various platforms. As well as IPv6 CP. I haven't seen consistency across the Cisco LNS feature set, as it were. And I'd be very interested in perhaps an update to that if you have the option at some point after the talk. The second question I was going to ask was, have you seen any overall on your LNS UNI transport from the PTT, any significant differences between your V4 days and now going dual stack in terms of overall background noise, if you will? Additional messages are flying around. We're handling additional IP6 protocol overheads, RA, PD, whatever. Is there additional floor of load that you see in your back-end systems that's significantly different from how it was in the V4 days only?
Okay. I'll go to the second question right away, and then return to the first, if that's okay with you. Like I said, at this point we have not enabled the service for everyone, right? So there shouldn't be, there are not significant traffic increases. Of course, if and when there is a traffic increase, we don't have to. We won't have to look at the ISPs or the PTTs because the Greek Research Network is the uplink. So we have all the. We're the infrastructure, right? Does that cover your?
Got it. I thought perhaps there was a telecom interconnect somewhere that I wasn't aware of. I was making the assumption that the use of
the ISPs, which you can see on the lower left side, are only doing administrative tasks, like they register the users, they do all the billings and all the, the bills. They're not doing any, and they are maintaining the passwords.
Got it. Thank you.
Sorry, the first question was?
If you could perhaps update the talk later on or send a few notes to the NANOG user list or something appropriate.
Yeah, no problem.
To just drop some relevant config details in their notes.
Yeah, the virtual interface, the virtual template configuration is quite simple. I mean, there's this, of course, IPv6 enable command, and then there's also a command that says do not suppress the router advertisements. But I can send a snippet. It's not problem. It's no problem. You can catch me later if you like.
Sure. The only reason I mention this is that there is a dearth of consistency across the various PRE, 10K, UBR, anything that does LNS features, and I haven't seen a single consistent config work across a variety of these platforms yet.
Yeah,
so.
yeah. Now that you mention it, the 10,000 is a whole different story. This is Cisco IOS software based 7300. So yeah, I agree with you. If we had a 10,000, it would be maybe it would be somewhat different.
Jari Arko Eriksson. So this was very interesting, thank you. I did have one comment though. You said that prefix delegation was your second choice after ND proxying. I actually think prefix delegation was the right choice, and that is something that you should do or should have done anyway. It's not, ND proxy has some limitations. It doesn't work for all security mechanisms that we have for IPv6. And if you do prefix delegation from day one, that allows you to later on increase and provision address space for your users in a flexible way. So I think that's the right architecture. It's also, I believe, the architecture that was or is in the Broadband forum plans when they are looking at the DSL IPv6 in a more general sense.
Okay, our main goal, I agree with you. Okay, and thank you for your remarks. Right, the main goal here was to try to minimize IPv6 prefix expenditure, right? Because what I really like about ND proxy is that you only use one prefix. And okay, this is ridiculous, probably, because
I think it is ridiculous. Actually,
it is ridiculous because this is IPv6, so we're supposed to have infinite addresses at our disposal, right?
It's not
as you can see, it's only 16 bits. So we had to make sure that we're not spending prefixes like crazy. So that's why I like ND proxy. But your remarks are.
Other considerations overweigh those address burning concerns, and you weren't burning them like crazy anyway. So there's other applications that burn them at a far higher rate. Right. I think it's very reasonable to assign the /64 or multiple /64s to a subscriber. Our
team has also worked on the Greek school network. This is not the Greek student network. The Greek school network provides access to the elementary schools and that kinds of and high schools. And it was much simpler because each school has a router which is administered by us. So we have set up DHCPv6 there, but everything static. DHCPv6 static, PPP static, everything. And when this is absolutely, there's absolute control over the expenditure of IPv6 prefixes. I agree with you. There's absolutely no problem with DHCPv6 prefix delegation. In fact, in some ways it's beneficial because you can use other lengths other than 64, right? So
that's right.
I agree. So I agree with you. On principle.
Okay. Thank you.
Thank you.
Okay, I think
I'll have maybe I'll have to discuss this BGP issue again, because this is the second time I'm hearing. Maybe there's something which should reconsider there. Right?
Sounds like a possibility, and maybe a talk at a future NANOG. Okay, well, we are. Whoops.